Hello, welcome back to Maths with Armien. In this video lesson, which is the last part of the differential calculus, part 5, we're going to look at optimization and then some real-life optimization applications. Firstly, we're going to look at the concept of optimization. Then we're going to look at what are the essential concepts and skills you require to do optimization. And then we're going to do two types of optimization applications. The one I refer to as direct, and the other type will be indirect optimization applications. And then as usual with all my video lessons, there'll be an exercise worksheet based on these concepts and skills. Let's start with the first unit there, the optimization concept. Optimization is a process of modeling a situation or a problem by means of a function, then applying differential calculus techniques to determine the most appropriate input value or values, right, which we will then use to determine the required minimum or maximum output values for the situation. Let's look at some real life examples to illustrate where optimization would be applied. Determine the minimum and maximum dosage of a medication. If you're a medical doctor, you want to prescribe some medication for that patient, it's important that if you prescribe too little, that medication might not have any effect. Or on the other side, if you prescribe too much, it can be detrimental to the health of that patient. Let's say that we have a water aquarium. If the water in that aquarium is too cold, then some of the fish or plants in that aquarium might not survive. On the other side, if the water is too warm, then you might have a problem again where other fish or other plants might not survive there. We want to determine the lowest cost of production. If you make something, it costs you something. So you want to try to have as high a production as possible, but you want to keep your cost as low as possible. You see, here we use a different word. Instead of minimum, we use lowest or least. Let's look at another example. You have a certain quantity of material and you want to make a container out of it. So you want to try to utilize that, the optimum utilization of that to make the largest possible container. You don't want to waste any material. On the other side, if, let's say, for example, you want to make a container with a fixed size and you want to know what the amount of material you're going to use, then you want, on this case here again, if you have a fixed volume, you want to try to minimize the amount of material that you require to make that particular container. Now, before we're actually going to do some examples on optimization, let's go over what are the skills and concepts that you require to be able to do these optimization problems. Let's look at the essential skills and content that you will require for doing optimization problems. The most important one is your differentiation rules and the different notations that will be used. Let's look at this one here. We use the ddx notation and we have ddx of the power x to the n. And how do we apply the power rule here? Nx to the n minus 1. Right? And we can use the ddx notation or we can use the prime notation as well. Then it will be essential that you know how to determine function values, in other words, substituting into a function. And then some of the problems will relate to 2D and 3D shapes. And in some of these shapes here, except the cones and the sphere, you must know the surface area or the perimeter or the volume of these shapes, except in the case of cones and spheres. If these shapes are used in the question, the formula for the surface areas and volumes will be provided. Then there are some basic algebraic skills that are necessary. How to expand, how to factorize, how to substitute, and how to simplify. And then in all these problems here, it will be essential for you either to solve a linear or a quadratic or a cubic equation. So you need to have the skill here. And then lastly, your calculator skills need to be tops. Let's look at the different types of optimum values. Let's consider a cubic function f over the finite interval a to d as illustrated here. You see finite, in other words, it has a starting and it has a end point, and these are fixed, it's not infinite. Now let's consider the point P. What type of point is P? That's correct. P is a maximum, but a local maximum. Right? And with P we have a value associated with it, corresponding x value, in this case B. What do we refer to that B? That's right, that is a critical value. Right? So we have a local maximum and a critical value associated with that. But let's look at another point up here. There we have point Q. This Q here, this is the local maximum, but Q is the corresponding y value there is much greater. So this one here is actually known as the, what did we refer to it in sketching? That's right, the true maximum or a absolute maximum there. And this one here is associated with the endpoint, and that is the value x is equal to d. Now point S, what type of point is S? That's right, S is a local minimum, and we have a critical value associated with it. In this case, x is equal to c. Now if we look at t, if this is the local minimum, t here has a value lower than the s value there. So this t here is actually the true minimum, or we refer to it as the absolute minimum. And in this case here, it is associated with the x value, x equal to a. Now if you look at our turning points P and S, there with the turning points P and S, we have that the first derivative is equal to 0. Why? Because if I have a tangent at P or a tangent at S, the gradient at that turning point P or this turning will be equal to 0. And you know, gradient of a tangent is actually the first derivative. And this is going to be our key. Working out turning points, working out local maximums or local minimums, we're going to determine the first derivative and equate it to 0. Now, let's look at the procedure for doing optimization, the general procedure. Before we actually do the general procedure, sometimes you have geometric situations or geometric problems. If diagrams are not given for these geometric situations, it is very useful to draw a diagram to assist you. First of all, in the problem, identify the constraints, identify the given information. Then, what is going to be now crucial here is to determine an objective function that needs to be optimized. But what is essential is that this objective function must be in terms of a single variable. Then now we're going to apply our differential calculus. We're going to determine the first derivative. And what goes with the first derivative when we have optimum values? That's correct, we have to equate it to 0. So the first derivative needs to be equated to 0 because at either local maximum or local minimums, the first derivative is always equal to 0. Then this is an equation. So we will be required to solve the equation. In other words, we'll have to determine the critical value or values depending on the equation there. And then once these critical values are obtained, then we can determine the required optimum values. But in all problems, please read your question carefully, because sometimes they only ask you to find the critical value. In other questions, they actually want to determine the specific optimum values. So reading a question is going to be very important. Don't do unnecessary, or don't forget, and then you might leave out the last part of the solution there. Now we're going to actually start doing some optimization problems, right? The first one is the direct optimization. But what do we mean by direct optimization? Or what do I mean by direct optimization problems? A problem is, I refer to a problem as being direct if the objective function is given. In other words, you don't have to determine an objective function. The objective function is given and it clearly states what type of optimization is required. And the constraints are always provided. An indirect application problem, again, is one where the objective function is not provided. In other words, you have to derive the objective function, or sometimes you have to show that a given equation or a given expression is the objective function. Or constraints will always have to be provided in this question as well. We start off with looking at the procedure for direct application problems. In the case of a direct application, the objective function is given. So in other words, we can immediately start with the optimization procedure. First step, determine the first derivative. Next, what do we have to do? That's right, equate it to 0. And once you equate it to 0, the next thing is that's an equation, so that we have to solve the equation. In other words, determine the critical values. And once you have the critical values, you can then determine the required optimum values there. But again, always read your question. This is I'm going to emphasize a lot. It's important here that you read the question, go back and see whether you've answered the question. Let's take some examples now. Let's look at the first one. We have an industrial process that requires water flowing through a cooling system, and the rate in liters per second at which the water is flowing through the system, and the time here is in seconds, is given by an equation. So here we have what we're given by. This is our objective equation that we have there. Objective function defined by this equation. Now the question, determine after how many seconds will the water be flowing at a maximum rate. So maximum, this is what we want to do. We want to determine the maximum of what? The maximum rate. So what needs to be optimized? It's the rate that we want to optimize, right? So we'll take the objective function and we'll optimize that. So let's look at the solution of this problem here. First of all, that's the given objective function. Okay. And we know here that because it's time, and this is a real life problem, time will be greater than 0. So that is the constraint that we have there. Now we have to determine the first derivative and equate it to 0. So let's differentiate that. That should be quite easy. Negative 0,4t plus 10, and then we equate it to 0. Very easy. This gives us a linear equation. And this should be very easy for grade 12s to be able to do that. So we transpose the 10 and divide by the negative 0,4. And this gives us, that's right, 25 seconds. T is in terms of seconds. And what did we say we always have to do here? Don't forget to read. After how many seconds? So we have to read. So have we answered the question? That's right. T is equal to 25 is our answer there, right? Let's look at the second example. A manufacturer has a capacity or the ability to produce 8,000 TV sets weekly. What do we mean by has the capacity? That's right, can produce up to 8,000 but not more than 8,000. So there we have from 0 to 8,000. The profit in rand earned if n TV sets are sold is given by, and there we are given an objective equation there. Now, determine the number n of TV sets to produce weekly to maximize the profit. So in other words, here we have that the profit equation is given, that has to be maximized, right? Let's look at the solution now. So let's start off with the given objective function. So the first thing that we have to do, that's right, we have to determine the constraints. And the constraints here, as we mentioned, n is a value somewhere between 0 and 8,000. So first of all, we differentiate and equate it to 0. Let's try that. Let's see whether you get it right. Give you a chance. That's correct. Negative 0,24 n plus 300 equal to 0. And here I've used the dp/dn notation here. Now that's again a linear equation. Should be quite easy, very easy. So we transpose the 300 and then we divide by negative 2,4, and this gives us n equal to, that's correct, 1,250. So what must we always do? Don't forget to read the number of TV sets. What is this? So the number of TV sets is, so we've answered the question. Always read your question. Let's look at example number 3. We have a particle moving along a straight line, particle or object, and the distance, which is given in meters of the particle from a fixed point on a line at time in terms of seconds, is given by, there we have an objective function. Question: determine after how many seconds the particle will be closest to the fixed point. Closest, what does that mean? In other words, that's correct, nearest to the fixed point. And what does that actually mean? The minimum distance to the fixed point. So we don't always use the word minimum and maximum. It's not always used to have words synonyms to the words minimum and maximum. So be careful of that. Now let's look at the solution now. First of all, we have our objective function which is given. And what are the constraints? What is the variable? The variable is t. And t stands for time. And in this situation here, time must be greater or equal to 0. Now we're going to determine the first derivative. Quickly do that. Give you 1 second. That's correct. 4t minus 18 equal to 0. Extremely easy. Linear equation. Solve it. 4t equal to 18. And therefore t is equal to, it will really be embarrassing if you make any mistakes here with solving linear equations. So please be careful, right? Please be careful with that. Don't make any mistakes there. And we always said that we have to read. Let's read it again, the question. After how many seconds? And we have t equal to 4,5 seconds. Therefore, we've answered the question, right? Always read your question. Let's consider one last direct application example. We have the surface area of a right cylindrical pillar with a hemisphere on the top, which needs to be painted. The complete pillar needs to be painted. The total exterior surface area in meters squared of the painted surface is given by, so there they give us an objective function. And now the question, determine the value of the radius or the length of the radius so that the least amount of paint will be required to paint the surface. Again, there you can see least amount. Also could have used lowest amount, or we could have used, that's right, the minimum amount, right? So let's start. There we have the cylindrical pillar, just to give you an idea. They normally would provide you with a diagram. So there we have a cylinder and we have a hemisphere, half a sphere on top there. So that we have a objective function, and here we have the variable r. R is the radius. What do we know about radius? Radius has to be a positive measurement. I mean, if you have a radius of 0, then you don't have a shape there. So the first thing, first procedure, that's correct. Differentiate and equate it to 0. Let's do this one. We have to be just a little bit more careful with this one. Differentiate that, give you a chance, and differentiate the second term. So let's see. The first one there is 4 pi r with negative 1, 2, and the negative 1 becomes a negative 2. Basic differentiation skill there. This one here is not a linear function, so let's be a little bit more careful now. We transpose the negative term, but the r to the negative, we can write that in terms of divided by r squared. That negative exponent, we can write it in the denominator, it becomes r squared. If it's like this, it's much easier to simplify. What can we do here? That's correct. We can multiply both sides by r squared because r is not 0. So that's or you can also say let's cross multiply. So if we do that, we end up with 4 pi r cubed, and we want to find r, so we have to make r the subject. That's correct. We have 1 comma 2 divided by 4 pi. Now if we have r cubed, how can we determine what is the inverse of cube? The inverse of cube is cube root, so we determine the cube root. And then depending on the question, they want you to give it to the nearest 2 decimal places. We can find the answer. There's it 0,46. And just be careful there. They mentioned here that the radius is in, the measurement there is in meters. Yeah, meters there. There's it meters squared. So the radius there is 0,46 meters there. And let's read what they asked, the value of the radius. Did we answer the question? Yes, there we have the value of the radius. So always remember to read. Just make sure that you're answering the specific question. Now we're ready to go one step further, and let's look at indirect optimization applications. Let's go over the general optimization procedure. We have to identify the constraints. In other words, read our question carefully. Then we have to determine an objective function here, and the objective function has to be in terms of a single variable. And then what do? So we differentiate, determine the first derivative, then equate the first derivative to 0. That gives us an equation. So we'll have to solve the equation, and that will give us our critical value or values. And then we can determine the required optimum value. And always don't forget to read your question. Let's start with our first indirect application example. The sum of two numbers x and y is 60. Determine the two numbers such that their product will be a maximum. So the sum of two numbers, in this case x and y, is 60. So it's their product that we need to maximize. As you can see, why it's indirect. What is missing? There's no objective function provided. So let's start off with identifying the constraint equation. What is given here? The sum. What does sum mean? Adding the sum of what? Of the two numbers. So what will what equation can I obtain from that? The sum of x and y is 60. Let's write it in algebraic notation. Sum is 60. So x plus y is equal to 60. Therefore, in this case here, we want to work with one variable, and you can either make the x or the y. Let's make y the subject. So y is equal to 60 minus x. Then if we read further, the product. So what needs to be maximized? The product. So our objective here is the product. What does product mean? Multiplication. Multiplying what? That's correct. The product is x times y. But here we have two variables. And what did we say about the objective function? One. So we need to replace one of the variables. This y here, we can replace it by a 60 minus x. Remember, it must be in one variable. So that y we replace with 60 minus x. We expand that, and there we have the objective function, 60x minus x squared. Now what do we have to do once we have the objective function? Determine the first derivative and equate it to 0. So there we have p prime, using the prime notation, 60 minus 2x equal to 0. Extremely easy, linear equation. Solve the linear equation. We end up with x equal to 30. What must we always do? Read. They say find the two numbers. Did we find two numbers? Only the one number. What is the other number? Let's go back. Y equal to 60 minus x. And x is 30. That gives me 30. So always remember to read your question. They don't ask us to work out x. They want us to find the two numbers there. Let's look at our second example. We have a rectangular plot having an area of 600 square meters. So there we have a rectangle, 600 square meters. That needs to be completely fenced. What do we mean by completely fenced? We put a fence here, and the fence there, and the fence there. Is that complete? No. We have to go right around where we end where we started. So that is the measurement. And what do we refer to this measurement? Perimeter. Peri means around and meter means measure. So perimeter, you say that as the perimeter, right? Let's read further. Determine the dimensions of the plot if the length of fencing. What do we mean by the word dimensions? Dimension means measurements. What are the measurements? The length and the breadth. In this case, the x value and the y value. If the length of fencing, now what is this length of fencing? That is, the perimeter needs to be minimized, right? So it's important that we read our question carefully. Now let's start. First of all, we need to identify the constraint, the given information. What is given there? 600 meters squared. What is that? The area. What's the area of a rectangle? Length times breadth. In this case, xy equal to 600. So we can either make here the x or the y the subject. Let's make y the subject. So y is equal to 600 divided by x. Now what is our objective? The perimeter, right? And what is that perimeter? Perimeter there would be x plus y plus x plus y, which in this case would be 2x plus y. We have two unknowns. And remember, we always need to have one variable. So we have the y, so we can substitute the y. So we only work with x. We can expand that, and there we have 2x, and 2 times 600 is 1200. But instead of dividing by x, we can write it in as x to the negative 1. It's much easier to differentiate if we have a power there and a power there. So let's differentiate and equate it to 0. I use the dp dx notation here. So that gives me 2 negative 1200, and x to the negative 1 becomes x to the negative 2. Just be careful with this equation, it's not a linear one. So I can transpose that negative 1200 x to the negative 2. But instead of writing down x to the negative exponent, let's write it as a positive. It's much easier if it's in the positive form there. To simplify this, we can multiply by x squared, or you can say also you can cross multiply. That gives us 2x squared equal to 1200. We want to solve for x, divide by 2, and then we have to find the square root of 600. Now usually when we have x squared, we always put what here? A plus or a minus. Now did I leave out the plus or minus, or is this correct? What is x? X is a length. Length can't be negative. Therefore you don't put in plus or minus here. We can write that square root of 600 in a simplified surd form, or we can write down its decimal equivalent there. Okay. Now, what is always important? Read, right? And if we read now, they ask us for the dimensions. That means I must find the x as well as the y. So we now find the y. We can do that by substituting. So I can go back there, substitute the x value, and simplify that. And there we get the value here. We can see in this case that both the x and the y, they are equal to each other. So the ideal shape here would be, if I want to minimize the perimeter, I need to have a square shape. Yeah. Now you're ready for the third example. We have a length of wire, 50 centimeters, and it's cut into two unequal pieces. Give me an example of some unequal pieces. That's correct. 10 and 40, or 20 and 30, or 3 and 47, or 2,5 and 47. So we can have various ways in which we can cut that length. Now what must be done with those two pieces? The first one is bent in the form of a square, and the other length is bent in the form of a circle, right? So after cutting them, we bend it, form a square, bend it, the other one becomes a circle. Now, determine the length of each piece such that the sum of the area of the square and the circle will be maximized. So we want to optimize the sum of the two areas. So that area plus that area, we want to optimize it. Now let's look at the solution. Let's just copy the question down again. First of all, we have a 50 centimeter length of wire. We're going to cut it The length is unknown at this stage. So let the one length be equal to x, and the other one would be, that's correct, other one would be 50 minus x. So we use the x for the circle, and the other piece we said is going to be 50 minus x, and we're going to use that piece for the square, right? Now we're putting it right around, and what do we refer to the measurement right around? Perimeter. What is the perimeter formula for a square? That's correct, 4 sides. And the perimeter for a circle, let's just also go through that again. That's correct, 2 pi r. So let's start with the square first. So the perimeter is 4 sides. So what will the length of one side be? Perimeter divided by 4, which means 50 minus x divided by 4. And the other pieces for the circle. So this circle's formula we said is 2 pi r. So what will r be? The circumference divided by 2 pi. What is the circumference measurement here? X. So r will be x divided by 2 pi. There. Okay. So there we have expressed the side of the square and the radius of the circle in terms of x there. But what is our objective? We want to maximize what? We want to maximize the sum. The sum of what? Sum of the areas. So we take the area of the square and we add it to the area of the circle. Come, what's the area of a square? That's correct, side squared. And the area of a circle? Those are formula you must know. It will not be provided in an exam. So area of a square is side squared. Area of a circle is pi r squared. But we always said we want to find one variable. So in other words, the s is 50 minus x over 4 squared, and the r is x over 2 pi squared. We just need to simplify that, and if you remove the brackets there, multiply out, we end up with this expression here. Okay? I'm just leaving that out because there's not enough space on the screen here. But just be careful. Sometimes with questions like this, they might just ask you prove or show that a is equal to that. In case you make some calculation errors there, at least you can use this part there. We have to expand that, and this is the objective function. Once we have our objective equation, what do we have to do? Differentiate and equate it to 0. So let's differentiate this. Derivative of that would be 0. The derivative of that would be negative 6,25. And what's the derivative of x squared? 2x. So let's see. So we have negative 6,25. And there we've got our 2x. And there we have our, because this is a constant. So it's 2x times that. Remember your differentiation rules. Now that's an equation. And this equation looks a little bit complicated. But it's actually a linear equation. Okay, there's just the x. Just the... Some of the values are a little bit not so cosmetic. So I transpose the negative 6,25. And if I want x, I need to just divide by that coefficient. And that will be 6,25 divided by that coefficient. This is calculator work, remember, and be careful with that. And we calculate that. That gives us approximately 22 centimeters. We get it to the nearest centimeter. Now, always read. We want to find the other piece, which is 50 minus 22. In this case, it is 28, right? So always remember, don't forget to read your question there, right? They don't just want the value of x. They said find the length of each piece, not just the one piece, the length of each piece there. I think you're ready now for example number 4. We have an open box with a square base made from 900 square centimeters of material with dimensions as shown. Okay, before we show you the dimensions, let's see what we understand by open box. What's an open box? That's right, a box with no top or a box with no lid. Let's look at that. There's it. You can see it's open. You can see, right? You can see that edge on the other side there. It wasn't open. We couldn't see that edge there. So there's the open box with dimensions as shown. In other words, they give us the height and they give us the x and the x. Well, they told us it's a square base. The question, determine the dimensions. We know by now, dimensions means we want to find the height and the side length there, or the h value and the x value. And we read further, the volume needs to be maximized. So let's see there. What is the constraint equation? What is given? 900 square centimeters, and that is a surface area. How many surfaces do we have for this open box? We've got a base, which is x by x, and then we have h by x, h by x, and at the back also h by x, and on the left side also a. So we have 4x plus h's. So in other words, the total surface area, TSA, will be 4x plus h, the 4 sides, plus the base, which is x squared. And that is given as we're limited to that. It has to be 900 square centimeters. Now there we have two variables, so we either need to make the h or the x. Now which one is the easier one? Let's correct the h there. This is a square, so it'll be more complicated. There's an x squared and an x, so it's much easier making the h the subject. To make h the subject, what do we get? 900 minus x squared divided by 4x. Now we sorted out our constraint equation or constraints. We now need to find the objective. Now let's read. What's the objective? It's the volume. And what's the volume of a rectangular box? Area of the base times height, which in this case is x squared times h. Again, we need to have one variable. So in other words, we can replace the h. We replace the h. That's what we get. So now we need to simplify. And if I remove that, give you a chance. Let's see what you can get there. That's correct. We end up with 225x minus 0,25x cubed. Let's see, how did we get that? X goes into that x, and 900 divided by 4 is 225. X times x squared is x to the 3, and 1 over 4 is 0,25. Right? It's much easier having it in this form than in that unsimplified form there, because we want to differentiate. And let's differentiate that. What's the derivative of that? The derivative of that is, that's right, 225. And the derivative of this, give you a chance. Don't use your calculator. It's embarrassing if you use your calculator here. 0,75x squared. 3 times 0,25 is 0,75. We then have a quadratic. Just be careful. We transpose the one term divided by 0,75. And to make x the subject, so that will be the square root. Again, x is a length, so it's a positive measurement, not a negative. You can use our calculator here, calculator work. You get 10 root 3. Now we've answered the question. No, you must read. And what does it say? Determine the dimensions, plural. We only determined one measurement, which is the length, the side length of the square. We also have to determine h, and where is going to get the, there we can get the h there. So we substitute x is equal to 10 root 3, and we put that in the calculator, and there we end up with 5 root 3. So there we've answered the question. In the next example, we're going to look at another geometric shape, in this case a cylinder. So we have a cylindrical metal can with a volume of 300 centimeters squared, as shown, that needs to be designed. Determine the dimensions of the can such that the cost of the metal to make the can will be minimized. So it's actually the cost of the metal, so that will be the surface area that needs to be minimized. What is given? We are given the volume. And what is the volume? 300. And the volume formula for a cylinder, this is the formula you need to know, and that is pi r squared times height. We have two variables. You can see which one will be the easier one to make the subject. That's equal to 300. So we make h the subject here. So that's 300 divided by pi r squared. Now that is our constraint equation. What needs to be optimized? The amount of metal to be used, that will obviously influence the cost. So that is the surface area. And what's the surface area formula for a cylinder? So we have a circle on top and a circle at the bottom. So that gives us the 2 pi r squared, and the measurement around, which will be the perimeter times h, which is 2 pi r h. We want one variable. It's always important, one variable. So we need to replace the h, and that's what we get there. We need to simplify that. You can see the pi and the pi there will cancel. That r can cancel that r squared. So we end up with a simplified version, 2 pi r squared. And that will give, instead of saying divide by r, we write down r to the negative 1. 2 times 300 is 600. So there we have our objective equation. We want to differentiate and put it equal to 0, dA dr, or you can say a prime. Differentiate 2 pi r squared becomes 4 pi r, and that one now we should get used to that, which is negative 600 r to the negative 2. Just be careful. Let's transpose the negative term. Instead of writing r to the negative 2, we write divided by r squared. About the third time that we've encountered this. We multiply by r squared or cross multiply. We make r the subject. So r is equal to the cube root. Remember, this has to be positive. You can either leave it like that or get the decimal version, 3,63. We read our question. We also want to determine h. Right, so we have to read that, and that gives us 7,25. So we saw that the one dimensions, we need both the r and the h. Let's look at one more geometric application, but this one involves the shapes of a cone, and you also have a sphere here. So in this particular example here, the formula will have to be provided. In this case, we've got two formulas. They don't mention which one is the cone and which one is the sphere. You need to know. They'll give you the formulas, but it won't be mentioned that this one is the sphere and that one is the cone. The formula is just given in this form. So let's see there. We have a right cone. So what do you mean by right cone? In other words, that from the apex there right to the center of the base, that will be perpendicular. It won't be slanted. R is the radius. There we have the radius of the cone is R, and the height AB of the cone is, there's the AB, the sphere with center O, and the radius of the sphere again is 8 centimeters. So there's 8 centimeters. You see another 8 centimeters. There's another, that's also another radius there. OB is X. Now there's the question, calculate the volume of the sphere. And then you see here they guide us with first step and then the next one, and then we're going to determine the volume. Let's see the question here. What needs to be optimized? It's the volume. Instead of maximum, we use the word largest, right? And it's a cone that's inscribed in the circle, the largest cone. Because I can have small ones and big ones, but we want to see what is the largest right cone that can fit in that sphere. Now let's proceed to the solution. Let's have the diagram there to assist us, and that's the first question. Volume of the sphere, that's a formula that's given. So there is your formula, 4/3 pi r cubed. And what is the radius measurement of that sphere? The radius, you can see the radius of the sphere is 8, so we substitute the 8, and we simplify that, and there's the volume of the sphere. Quite straightforward. Let's look at number B. Show that r squared equal to, now let's just see where's r squared. There's r, and there's the x, and what does that give me? Remember we said this is a right cone, so this angle is 90. A right angle triangle we associate with, that's perfect. Very basic, Pythagoras. So let's apply Pythagoras in that triangle. So that's r squared plus x squared equal to 8 squared. Make r the subject, r squared the subject, and there we end up with that. So it should be worth 1 mark only. Number C. This is going to help you step by step here. Number C, determine the volume of the largest cone. Volume of a cone, the volume formula was given. So now we just have to substitute. What is the radius measurement of the cone? The radius is, there's the radius. Radius is r, so we keep the r. But the h and r here, we can see r is in terms of, there's r squared. I can replace the r squared. H is the height And what is the height? The height is AB. And what's the length of AB? Not 8x, but 8 plus x. So r squared, I replace the r squared, and I replace the h, which is 8 plus x. We need to expand that so that it will be easier for us to differentiate. If we expand that, we get this cubic expression there. Okay, just be careful while you expand that. And then now we want to start with the optimization. We need to differentiate. You can either say v prime, and that's a constant, it remains a third. Derivative of 512 is 0. Derivative of 64x is 64. The next one is negative 16x, and the last one negative, and there's my answer. So there I have a quadratic equation. And solving a quadratic equation, what are the known methods there? Factorization, that's a bit complicated. You use your quadratic, or you can even use your calculator, depending on the type of calculator you have. So I leave that up to you to determine whichever method that can. And then eventually we end up with, after solving that quadratic, we end up with a positive x value. A negative value we discard. So x in this case is 8 over 3. And now let's read the question. We want the volume, not the x value. So I have to go back to my volume formula and I need to substitute. So there's the volume formula. And I put 8 over 3 in there. Remember we said calculator work, you need to be careful. Calculate that, write down your answer. And I suggest with this, just clear your screen on your calculator, re-enter it and calculate. And if you get the same answer, you know you're correct, right? It's rather be safe because so easily you can make a mistake, or just do it carefully. As you type in, don't rush, make sure there's a square and there's a cube. So there we've answered that particular question. Okay, and remember we always try to read our question. Always. So that's the volume. And we see, yes, we've worked out the volume, right? So always read just to make sure that if they ask you here, determine the value of x, that will be something different. But here they ask you determine the volume of the largest cone. That's the end of. Here if we have an indirect application which is a bit different to the previous ones here. Let's see. We've got a figure alongside which shows a parabola. You see there? There's a parabola there. But there are some restrictions to this parabola. It tells you that it's defined from 0 to 4. So it's only the positive side, 0 to 4. There's the parabola. And we have a point D. There's a point D with the coordinates. And we have BD, which is parallel, right? And because this is an axis, if this is perpendicular, then that must also be perpendicular there. To the y-axis, B is a point on the curve. And there we have some questions, and we'll go through those questions there. We say as large as possible. What would that mean? That would mean that we need to find the maximum there. So that's the question. Let's look at the solution here. There's our diagram. Write down, right? So this should be quite simple. The coordinates of B. So we need an x and a y coordinate for B. X is x. What is y? Fx is the same as y, right? And what was our fx? Fx is 4 minus 0,25 squared. So that's the coordinate. You can go straight from there to there, but just explaining xy, that means x fx, and fx you just replace the fx. Now the next question, show that the area of a triangle. The area formula of a triangle will never be given in grade 12, right? Area of a triangle, half the base times the height. What's the base of that triangle? That's correct, OD, and the height, BD. So there's the area of a triangle. Half OD times BD. OD's length is X. And BD is actually, we've just worked out, BD is the Y value, which is 4 minus 0,25 X squared. 0,25 X squared. We multiply that out, and we end up with this simplified version of this. Then, so there we showed the area. There we've answered the question. Let's look at the next question. Determine the value of x at the area, that area will be as we must determine the value so that we'll have a maximum area. As large as possible means the maximum one, because you can have many triangles. You can have a triangle down there, you can have a bigger one, so somewhere there's the largest, and we're interested in to know what should this x be. You can move that d along somewhere between 0 and 4. So let's see, let's differentiate that. That's very easy. So that's 2 minus 3/8 x squared. Simplify that, get the square alone, find x, which needs to be a positive value. Let's calculate it, and there we have the decimal equivalent of a 2,3, right? And let's read the question. We must determine the value of x. And did we find the value? Yes, we already found the value. And that's all we want. We don't want anything else but the value of x there. And that is the solution to. Now, before we want to start with the exercise worksheet, as before, I always recommend look at the worked out example, take the question. We had 4 direct ones. Take maybe most of them, do it on your own, and then you compare your solution. If you get stuck, you try to do it over again. And the same, there are 7 indirect ones. Don't just listen to it or just follow it. Try to do it on your own, and once you've done that, then you can start doing the exercise worksheet. Let's just go through each one of them briefly. We're not going to do the solution. In the first one here, you can immediately see we are given a objective function, so that should be quite straightforward. And here there are some sub questions. You'll try to do that on your own. This one here, again, you can see there's an objective function given and a number of sub questions. This here is the constraints. T must be a value somewhere between 0 and 10. Then there's something else. This one is a business one. The previous one related to something out of the health sciences. So there's the profit, and we want to optimize the profit. In other words, determine the maximum. This one there, we have a geometric one. Something similar here, it's just a piece and it's cut into 2 pieces. But here the one piece must be a square and the other piece will make a U shape to form a rectangle there. Different to the one where we had the circle and the. In this one here, we have a triangle and we have a rectangle. You can have many rectangles. You can have a small one there and a big one. So we want to know what should the K value be so that I can get a maximum area. You can draw many rectangles within that equilateral triangle. Here we have a solid right prism, and there are some questions. They help us. They tell you which one make H in terms of X. You have to see what is your constraints there, and then show that instead of just giving you the question directly like this, the C part, they help you show that the surface area. So you just have to show that's there. If it happens that you struggle to get that, just use this to answer. Just use this part of question number B to answer question number C there. Question number 7, again we have a box, similar idea, just some other information, and you have to, there's the objective function given, but you must show how the objective function was derived, and then you can. Here again another box with a different situation. There we have a net of that box and show how the box was designed. And there you have to determine the volume. They ask, this is the volume given, so you can. This is actually the formula that you have to use to maximize the volume there. Here we have a square and a semicircle, and this is the floor of a stage. You just read through that step by step, determine inspection for B, and then find it. So here you have to determine your objective function. No objective function is given here. Very basic shapes. Rectangle and a semicircle. Here we have a cylinder similar to what we did earlier. I think the other one was 300 cubic centimeters, and here we give it in milliliters. It's a known fact, something that you need to know. 1 milliliter of water at standard temperature and pressure is 1 cubic centimeters there. The physical science learners should appreciate that. There's some questions again with a. They must show how, this is the objective function, but you must show how it was obtained. But you can use it to answer this. Then we have another one, something different. They're also being helped. They have to show that the area, and you can actually use it as quite a lot, so you must show how was that area determined. But if you struggle to get that, just use it to answer the B part there. Here we have something similar, a little bit different. Again, a cone inside a circle, but it's a totally different situation there. And then we have something similar to our question number 7. We have a graph, and they ask you a few questions. Find the coordinates of P, and here we want the distance from P to P. These are the 13 questions that I would recommend that you try all of them. And thank you very much, and I hope you have benefit from this series of calculus lessons, the 5 there. And I would also recommend that you look at some of the other videos that I've created for grade 12 CAPS mathematics. Thank you very much.